Hello dear students, welcome to the ACE online platform. I am Malakondaya Gandham. In this platform, we are going to discuss the detailed solutions for the very old questions which were asked before 2000 from the thermal part. Okay, shall I take the very first unit? Yes, that is the Zeroth law of thermodynamics and basics of thermodynamics. Okay, from that, look at the very first question asked for 1 mark in the year 1993. Very old question. The question is asking like this: a body of weight 100 newtons falls freely a vertical distance of 50 meters. The atmospheric drag is 0.5 newtons. For the body, the work interaction is, different options are available. Work interactions are given both negative and positive signs. As we know, work done on the system thermodynamically taken as negative, work done by the system should be taken as positive. Okay, next, what is the physical meaning of thermodynamic work? A kind of energy which is causing for lifting the load or carrying the load is called thermodynamic work. Once again, a kind of energy which is for lifting the loads or carrying the loads is called thermodynamic work. That is the one sense of thermodynamic work definition. The other sense is a kind of energy which is crossing the boundary of the system either by pressure difference or force difference can be called as thermodynamic work. That is another sense of definition for thermodynamic work. The other sense of thermodynamic work definition is the kind of energy which is crossing the boundary of the system other than temperature difference is coming under thermodynamic work. Dear friends, remember, the kind of energy which is crossing the boundary of the system only by temperature difference is called thermodynamic heat. Other than temperature difference, whatever the other energy which is crossing the boundary of the system is coming under thermodynamic work only. Okay. For this case, weight of the body given, weight of the body 100 newtons, and it is travelling a distance, let it be s, equal to 50 meters. 50 meters. And atmospheric drag force, that means the frictional resistance, frictional drag between the body and surrounding atmospheric air, that I am marking as drag force 0.5 newtons. As you know, by the time the body is falling down, because of the frictional drag only, the surrounding dust particles are thrown away. Therefore, thermodynamic work equal to frictional drag multiplied by the distance travelled by the body. Okay, frictional drag given 0.5, distance travelled is given 50, is equal to, it is equal to 25 newtons. That is the thermodynamic work. But look at the options. Minus 25 is available. Here work in thermodynamic work, force multiplied by distance. It is force is in Newton, distance is in meter, Newton meter. 1 Newton meter equal to 1 joule only. That 25 joules available with negative sign and positive sign. Here, by the time the body is falling down, the surrounding dust particles are thrown away from the body. That means work is transferring from body to outside. Work is transferring from system to surroundings is taken as positive. Therefore, plus 25 Newton meter or plus 25 joules is the absolute correct answer. Understood clearly? I am trying to explain the each and every point at your understanding level. Okay. Similarly, let us take the another question asked for, right, 1 mark only in the year 1993. It is asking like this: an insulated rigid vessel. Insulated means heat transfer Q equal to 0. That means that system is coming under adiabatic system. Rigid vessel means change in volume dV equal to 0. If change in volume dV equal to 0, you know the thermodynamic work for a closed system equal to PdV. Since dV is 0 for a rigid vessel, thermodynamic work is 0. Contains a mixture of fuel and air. That rigid insulated vessel is containing mixture of air and fuel, that means air fuel mixture. The mixture is ignited by the minute spark the contents of the vessel experiences. Here the air fuel mixture is available in the rigid vessel which is insulated, therefore that is taken as a closed system. For a closed system, energy balance equation is Q equal to W plus du. Q equal W plus du. Here Q 0, W 0, W 0. Therefore du is equal to 0. Du 0 means what? U2 minus U1 equal to 0. U2 equal to U1. That means the internal energy U remains constant. So for this process, for this fuel burning process, heat transfer Q0, work transfer W0 and internal energy remains constant. Look at the options. Increasing temperature, pressure and energy. Energy remains constant. Okay. As you know, as long as the energy remains constant, insulated rigid vessel containing mixture of fuel and a mixture. Okay. Energy remains constant, but it is given increase in temperature, pressure and energy. Energy cannot be increasing. Decrease in temperature, pressure and energy. No, right? A not correct, B also not correct. Increase in temperature and pressure, but no change in energy. That is looking correct. Because it is maintaining constant volume. Rigid vessel means change in volume 0. What it means? Volume remains constant. At constant volume, according to Gelasic law, pressure is directly proportional to temperature. Because of the burning of the fuel present in the system, temperature of the gas increases. Along with the temperature, pressure increases. So it given that increase in temperature correct, increase in pressure correct, but no change in energy remains constant. Therefore option C is absolutely correct. Understood clearly? Yes. Similarly, look at the next question. It is asking like this: the definition of 1 Kelvin as per the internationally accepted temperature scale is. Here the definition for 1 Kelvin. As you know, the point where the solid phase, liquid phase and gaseous phase of the same material can be coexisting under equilibrium state is called triple point state. Okay. For water, the pressure at the triple point state, for water at triple point state, pressure is 0.00611 bar and temperature is 0.01 degree centigrade. Of course, that is the thermometer reading. It is better to mark with the small t. This is for water at a triple point state. Okay. Then what is the absolute temperature? Absolute temperature of the water at a triple point state equal to thermometer reading in degree centigrade at a triple point state plus 273.15. What is the thermometer reading at triple point state? 0.01 plus 273.15. It is equal to 273.16 Kelvin. 16 Kelvin. It is equal to triple point temperature of water. Therefore, 1 Kelvin is defined as 1 by 273.16 times the triple point temperature of water. That is the 1 Kelvin definition. Once again, 1 Kelvin is equal to 1 by 273.16 times the triple point temperature of water. Now look at the options. 1 by 100, not correct. 1 by 273.15, the normal freezing point, not correct. 100 times the, no, 100 is not correct. 1 by 273.16 of the triple point of water. Option D is absolutely correct. Understood clearly? Yes. Similarly, look at the next problem. It is also asked in the year 96 for 1 mark like this. The specific heats of an ideal gas depends on specific heats of the ideal gas. As we know, according to Regnault's law, the ratio between the Cp and Cv remains constant. That constant is called adiabatic index. From this, you can write that Cp equal to gamma Cv. Cp equal to gamma Cv. Next, the Mayer's equation is Cp minus Cv equal to R. But what is the Cp? Gamma Cv minus Cv is equal to R. From this, write the Cv outside, gamma minus 1 equal to R. Cv equal to R by gamma minus 1. R by gamma minus 1. Here Cv is called specific heated constant volume. Similarly, you know, Cp equal to what? Cp equal to gamma Cv into Cv equal to R by gamma minus 1. It is equal to gamma by gamma minus 1 into R. Here R is called characteristic gas constant. Okay, but according to Avogadro's law, product of molecular weight and characteristic gas constant equal to universal gas constant Ru. That Ru standard value 8.314 kilojoules per kilomole Kelvin. From this, characteristic gas constant equal to 8.314 dividing by molecular weight. Okay, in the place of R, I can write that value. Now, first let me take the Cv value. Cv equal to R by gamma minus 1, but R equal to 8.314 divided by m into gamma minus 1, and Cp equal to gamma by gamma minus 1 into R value 8.314 divided by molecular weight. Now look at the Cp and Cv. The specific heats are depending on molecular weight of the gas and also the adiabatic index. The adiabatic index gamma is depending on the degree of freedom, that is the molecular structure. Degree of freedom, the adiabatic index gamma is a function of degree of freedom. That degree of freedom is depending on the molecular structure. From that, the conclusion is the specific heats of the ideal gas not only depending on the molecular weight but also depending on the molecular structure. That is the answer. Look at the options. Temperature, no. Pressure, no. Volume, no. Molecular weight and structure of the gas. Option D is absolutely correct. Understood clearly? Yes. Similarly, now let us take the 2 marks questions. It is the match list 1 with list 2 kind of question. Under list 1, look at the different quantities, cetane number, approach and range both are connected to cooling towers, dou T by dou P at constant enthalpy not equal to 0, dH equal to Cp dt even when pressure varies. Look at the list 2, ideal gas, van der Waals gas. Van der Waals gas means real gas. real gas. Let me write it clearly. Van der Waals gas is also called real gas. Real gas. Spark ignition engine, compression ignition engine, cooling towers, heat exchangers. Okay. As you know, the Joule-Thomson coefficient mu Jt, Joule-Thomson coefficient mu Jt equal to dou T by dou P at constant enthalpy. Now, for ideal gas, no, the throttling process is happening. Joule-Thomson coefficient is for throttling process. Throttling process is happening at constant enthalpy. That's why throttling process can also be called as isenthalpic process. Okay, that's why it is written dou T by dou P at constant enthalpy. Right, enthalpy remains constant in the throttling process means, for ideal gas, enthalpy depending on only temperature. Enthalpy is the function of temperature. Therefore, since enthalpy is the function of only temperature, in the throttling process, T1 equal to T2, final temperature and initial temperature both are equal for ideal gas. If T1 and T2 both are equal, dou T equal to 0. Dou T 0 for what ideal gas. Then what is the Joule-Thomson coefficient? Joule-Thomson coefficient is equal to 0 for ideal gas. But for real gas, enthalpy not only depending on the temperature but also depending on the pressure and volume. Therefore, for ideal gas, for real gas, enthalpy not only depending on the temperature but also depending on the pressure and volume. Therefore, right, for the throttling process, T2 need not be equal to T1. Therefore, dou T is not equal to 0. If dou T is not equal to 0, then mu Jt is equal to what? Dou T by dou P at constant enthalpy. This dou T by dou P at constant enthalpy, that is equal to Joule-Thomson coefficient 0 for ideal gas. For real gas, it is not equal to 0. It is not equal to 0. Now, having that information, look at that one. C10 number, the quality of the petrol fuel is measured in terms of octane number, whereas the quality of the diesel fuel is measured in terms of the C10 number. The diesel fuel is used for diesel engines are also called compression ignition engines. Therefore, C10 number connected to compression ignition engines. A4 correct. Next, approach and range. Both are connected to cooling towers. Approach means the difference between the water temperature at the exit of the cooling tower and surrounding atmospheric air wet balloon temperature is called approach. The difference between the water outlet temperature at the exit of the cooling tower and surrounding atmospheric air wet balloon temperature is called approach. Range is the difference between the, for the cooling tower, water is entering at a high temperature and water is leaving at low temperature. The difference between the water temperature at the entrance and exit is called range. Anyhow, approach and range both are connected to cooling towers. Therefore, B5 correct. Next, dou T by dou P at constant, this is the Joule-Thomson coefficient not equal to 0 for real gas. That is also called Van der Waals gas. dH is the function of dT, temperature, even when pressure varies. That means enthalpy change is depending on only temperature for ideal gas. Therefore, C2 correct, and D1 correct. That is the correct answer. Understood clearly? Yes. So, that is the correct answer. Now, look at the next question. It is asking like this. An isolated thermodynamic system executes a process. Choose the correct statements from the following. No heat is transferred, no work is done, no mass flows across the boundary of the system, no chemical reaction takes place within the system. As you know, the isolated system is one. Let this is the isolated system. If you want to call this system as isolated system, there should not be any energy interaction equal to 0. Energy interaction between the system and surroundings may be in the form of work transfer 0 and heat transfer Q also 0 and mass transfer 0. If you want to call a system as a isolated system, there should not be any mass transfer, there should not be any energy transfer. Here, since the problem is given for isolated system, isolated thermodynamic system, mass transfer 0, heat transfer 0, work transfer 0. No heat is transferred, correct. No work is done, correct. No mass flows across the boundary of the system, correct. Here A correct, B correct and C also correct. It is the MSQ type of question, right? MSQ type of question. Understood clearly? Right. So, these are the problems which were asked before 2000 from basics of thermodynamics and zeroth law of thermodynamics. I hope all of you clearly understood. Understood or not? Dear students, now let us take the problems from work and heat. Okay, look at the very first question asked for 1 mark in the year 1996, asking like this: for reversible adiabatic compression in a steady flow process, the work transfer per unit mass is, it is given for a steady flow process. As you know, the work interaction formula for a closed system is called non-flow work. That non-flow reversible work equal to integral 1 to 2 PdV. Dear friends, remember, it is for only closed system reversible process. For only closed system reversible process, you can use this formula for deciding the work interaction. But it is given for steady flow process, means open system process. For a steady flow reversible process, the steady flow work equal to minus integral 1 to 2 VdP. VdP is the steady flow work with negative sign and PdV is the non-flow work. It is given for reversible adiabatic compression in a steady flow process. Therefore, the steady flow work is minus VdP. Look at the options, right? Of course, right, negative sign is not considered. The right VdP option B can be selected, but original formula is minus VdP. Understood clearly? So, this is the PdV. It is for a closed system and it is for steady flow system. Option B is absolutely correct. Okay. Similarly, look at the 2 marks question asked in the year 93, very old question like this. A vertical cylinder with a freely floating piston contains 0.1 kg air at 1.2 bar. This is the vertically floating piston. The mass of the air given, mass of the material 0.1 kg. That material is available with a pressure P equal to 1.2 bar. As you know, 1 bar equal to 100 kilopascal. It is equal to 120 kilopascal. 120 kilopascal. And small electrical resistor. Look at the electrical resistor. This is the electrical resistor. The resistor is wired to external 12 volts battery. The voltage supplied to electrical resistor 12 volts. 12 volts. When the current 1.5 amperes is passed through the resistor, the current supplied, current is marked as I, 1.5 amperes, amps. Okay. And that resistor is carrying the current for the time period 90 seconds. Time taken small t equal to 90 seconds. Okay. the piston sweeps a volume of 0.01 meter cube. That means by the time the electrical resistor is giving the energy to the gas is expanding. By the time the gas is expanding, piston is traveling to a distance of 0.01 meter cube. That is the displacement of the piston. The displacement of the piston equal to 0.01 meter cube. Okay. Assume the piston and cylinder are insulated. Piston and cylinder are insulated. It means heat transfer Q equal to 0. Heat transfer Q equal to 0. Next, air behaves as an ideal gas. Air is treated as an ideal gas. The specific heat of the air given at constant volume 700 joules per kg. The specific heat at constant volume CV 700 joules per kg Kelvin. It is equal to 0.7 in kilojoules per kg Kelvin. Okay, kilojoules per kg Kelvin. Find the rise in temperature. What is the rise in temperature of the air present in the system? Okay, since it is a closed system, the closed system energy balance equation is non-flow energy equation. Q equal to W plus du. W plus du. Since the system is perfectly insulated, heat transfer Q equal to 0. Then work done, right, work done plus change in internal energy du equal to 0. From this I can write that du is equal to minus of work. Okay, but here there are two work interactions. The boundary work by the time the piston is moving away while the gas is expanding, and the energy given to the gas by the resistor. Energy given to the gas by the resistor is the negative work done on the system. The boundary work is coming under positive work because that is coming under work done by the system. Here boundary work is, I can say piston work is the boundary work. That piston work is PdV because it is a closed system. Closed system work equal to PdV. Look at the P value. 120 kilopascal, dV 0.01. 120 into 0.01, it is equal to 1.2 kilojoules. That is the piston work. This is the positive work. Boundary work is the positive work. Resistor work. Resistor is giving the work to the system, that is the negative work. That is equal to VIT. Resistor energy transferred to the gas. Here gas is our system. Voltage, look at the voltage. 12 into 1.5 into 90. 12 into 1.5 into 90. It gives in joules dividing by 1000 to get in kilojoules. It is equal to 1.62 kilojoules. Since the resistor is giving the energy to the gas is our system, work energy given to the system is taken as negative. This is the negative work. Then this work equal to net work. Work means net work. That net work equal to what? The positive work minus negative work. Positive work 1.2 minus 1.42, 1.62. Listen carefully, 1.62. It is equal to minus 0.42 kilojoules. That is the net work. So du, since it is asking air is taken as ideal gas. For ideal gas, internal energy depending on only temperature. This du is written as mCV into dt. It must be equal to net work. Net work is, right, minus 0.42. Right, dt equal to minus of minus plus 0.42 dividing by m. Mass of the gas is how much? Mass of the gas 0.1 kg. 0.1 kg, CV value 0.7. 0.7. You simplify this value for getting the temperature rise in the air as 6 degrees centigrade. That is the answer. It is asking the rise in temperature of the air. The rise in temperature of the air is 6 degrees centigrade. That is the answer. Understood clearly? Yes. Dear friends, only 2 questions were asked before 2000, right, from the work and heat. That is all about the work and heat previous year questions. That means very old questions. Understood clearly? Yes. Dear students, now let us discuss the detailed solutions for the very important unit, that is first law of thermodynamics. This first law of thermodynamics is also called law of conservation of energy. Okay, look at the very first question from the first law asked in the year 93 for 1 mark. It is asking like this: the first law of thermodynamics takes the form work equal to minus delta H when applied to. That means for which process, for which open system process, work transfer is equal to change in enthalpy with negative sign. That is the question. Okay. For that, as you know, for the open system, work interaction is called steady flow work. For a closed system, work interaction is called non-flow work. The non-flow work formula already we discussed. Non-flow work equal to PdV. Non-flow work is PdV. Whereas the steady flow work equal to minus VdV. Okay. The relation between the steady flow work and non-flow work is steady flow work equal to P1 V1 minus P2 V2 plus non-flow work. This is the relation between the steady flow work and non-flow work. Dear friends, remember, since non-flow work equal to PdV, area below the PV diagram is equal to non-flow work. Whereas steady flow work is minus VdP, therefore area behind the PV diagram, area towards the pressure coordinate in the PV diagram is equal to steady flow work. Okay. Now, if I take the reversible adiabatic process, for a reversible adiabatic process, for a reversible adiabatic process, what is the non-flow work? Non-flow work equal to P1 minus P2 V2 divided by gamma minus 1. That is the non-flow reversible adiabatic work. Then steady flow reversible adiabatic work. Steady flow reversible adiabatic work equal to P1 V1 minus P2 V2 plus non-flow work for a reversible adiabatic process, that is P1 V1 minus P2 V2 divided by gamma minus 1. Now let us simplify it. Let me write the P1 V1 minus P2 V2 outside into 1 plus 1 by gamma minus 1. It is equal to P1 V1 minus P2 V2 into here gamma minus 1 plus 1 by gamma, that is equal to gamma by gamma minus 1. Understood clearly? That means 1 plus 1 by gamma minus 1, you simplify it for getting gamma by gamma minus 1. Okay. Then it can be also written as, it is equal to, P1 V1 equal to RT1 minus P2V2 equal to RT2, ideal gas equation, into gamma by gamma minus 1. Okay. So that can be also written as the steady flow reversible adiabatic work is equal to what we got is, right, R T1 minus T2 R into T1 minus T2 into gamma by gamma minus 1. It is equal to R by gamma minus 1 into gamma into T1 minus T2. As you know, CV, specified constant volume, equal to R by gamma minus 1. In place of R by gamma minus 1, write the CV into gamma into T1 minus T2. CV gamma equal to CP into T1 minus T2. It is equal to Cp T1 minus Cp T2. For ideal gas, enthalpy depending on only temperature. Therefore, Cp T1 equal to H1, Cp T2 equal to H2. Finally, what we got? Steady flow reversible adiabatic work. Steady flow reversible adiabatic work is H1 minus H2. H1 minus H2. Generally, we are writing delta H or dH means H2 minus H1. Since delta H is H2 minus H1, steady flow reverse adiabatic work is H1 minus H2. This I can write as minus of delta H. Therefore, work equal to minus delta H only for a reversible steady flow adiabatic process. Okay, got that point? Now look at the options. A closed system, no, it must be open system. An open system undergoing an adiabatic process with negligible changes in kinetic energy and potential energy, absolutely correct. Dear friends, remember, the steady flow work is equal to minus VdP by ignoring change in kinetic energy and change in potential energy. That formula we are deriving by ignoring the change in kinetic energy and change in potential energy. Understood clearly? Anyhow, option B is absolutely correct. The remaining are given for closed system only, right? By looking that system, you can conclude that it is for only option B. Understood clearly? Yes. Similarly, look at the next question. It is asked in the year 1999 for 1 mark only, like this. A steel ball of mass 1 kg and specific heat 0.4 kilojoules per kg Kelvin is at a temperature of 60 degrees centigrade. Mass of the steel ball given 1 kilogram. Specific heat of the steel ball 0.4 kilojoules per kg Kelvin, and initial temperature of the steel ball is equal to 60 degrees centigrade. It is dropped in 1 kg mass of water. Mass of the water equal to 1 kilogram. Initial temperature of water is 20 degrees centigrade. That means the steel ball is dropped in the water. The final steady state temperature of water is, once the high temperature steel ball is dropped in the low temperature cold water, the high temperature steel ball is losing the thermal energy that is taken by the water. Finally, the water, 1 kg mass of water and 1 kg mass of steam, both are coming to thermal equilibrium by law of conservation of energy. That is, heat energy lost by the steel ball equal to heat energy gained by the water. Let me write that point here. The condition is, right, heat lost by steel ball must be equal to heat gained by heat gained by cold water. Finally, both are coming to thermal equilibrium at a temperature of Tf. That means the 1 kg mass of steel ball and 1 kg mass of water both are finally maintaining Tf temperature. Okay. Here heat lost by the steel ball equal to mass of the steel ball into specific heat of the steel ball, initial temperature of the steel ball minus final temperature of the steel ball, okay, is equal to heat gained by the water, mass of the water, Cp of the water. Here water is receiving energy, therefore final temperature of water minus initial temperature of water. Water temperature increases by the time the steel temperature decreases. Finally, both are coming to same equilibrium temperature. It means Tf for water equal to Tf for steel. Okay, na? Then here mass of the steel 1 kg, mass of the water 1 kg, these two quantities are cancelled. Specific heat of the steel given 0.4 kilojoules per kg Kelvin. Initial temperature of the steel 60 minus final temperature of the steel is Tf is equal to specific heat of water is constant at 4.2, that is standard value. The final temperature of water Tf minus initial temperature is given 20 degrees centigrade. Now you simplify it, right? You simplify it for getting the final equilibrium temperature, right? Your calculator will show that around 23.48 degrees centigrade is around 23.5, not 25, 23.5 degrees centigrade. That is the approximate answer. Look at the option A. Option A itself is absolutely correct. Understood clearly? It is completely based on law of conservation of energy, that is heat lost by the hot material equal to heat gained by the cold material. I hope all of you clearly understood. Understood or not? Yes. Then look at the next question. It is asking like this. A steam turbine receives steam steadily at 10 bar with enthalpy of 3000 kilojoules per kg and discharges at 1 bar with enthalpy 2700 kilojoules per kg. Better to mark the turbine. This is the steam turbine. For this steam turbine, let the steam is entering somewhere here and steam is leaving at this location. Given that enthalpy of the steam while entering is 3000 kilojoules per kg and while it is leaving, that I can mark as H2 2700 kilojoules per kg. The work output from the turbine is developing. The turbine work is given 250 kilojoules per kg. The changes in kinetic energy and potential energy are negligible. The heat transfer from the turbine casing to the surroundings is, that means the insulator may not be perfect, because of that some heat is transferred outside. Okay. Then how much amount of heat is lost to surroundings? That is the question. Very simple question, very simple 1 mark question. As you know, the turbine work, otherwise let us connect the energy balance equation. Some of the energies entering to the system must be equal to energies leaving from the system. Energies entering to system is only H1. Energies leaving from the system, right, H2 plus turbine work plus the heat loss to surroundings. Now this heat loss to surroundings equal to H1 minus H2 minus turbine work. H1 is 3000 minus H2 2700 minus turbine work is given 250. 3000 minus 2700, 300 minus 250. It is equal to 50 kilojoules. That is the amount of heat lost to surroundings, 50 kilojoules. Look at the option B. Option B is absolutely correct. Understood clearly? Yes. Then 2 marks questions. Look at the question asked like this. A rigid insulated cylinder. A rigid means work interaction 0. Insulated means heat interaction 0. Has a 2 components separated by a thin membrane. A thin membrane. It may be like this. This is the rigid and insulated vessel. Let me insulate it. It is perfectly insulated for avoiding the heat transfer. Heat transfer Q equal to 0, and rigid vessel na work transfer 0. And a thin membrane is separating. A thin membrane is separating the 2 compartments in the rigid vessel. Okay, that's why it is given. While one compartment contains 1 kilomole of nitrogen at a certain pressure and temperature. Let us take a minute. This is the compartment 1, compartment 2. So, compartment 1, assume the number of moles of the nitrogen is 1 kilomole, 1 kilomole, 1 kilomole with a certain pressure and temperature. That pressure and temperature not given. Okay. Then the other contains 1 kilomole of carbon dioxide at the same pressure and temperature. The other compartment is maintaining carbon dioxide, number of moles of carbon dioxide also equal to 1 kilomole at the same pressure. This pressure and this pressure both are same temperature. That means no pressure difference, no temperature difference, only right the left side compartment is maintaining diatomic gas like nitrogen, and the right side compartment is maintaining triatomic gas like CO2. Okay. Then the membrane is ruptured and the 2 gases allowed to mix. That means somehow this membrane is punctured or ruptured. Then the 2 gases are allowed to mix uniformly. Okay. Then assume that the gases behave in ideal gas. Calculate the increase in entropy of the contents of the cylinder. Universal gas constant equal to 8314 joule per kilomole Kelvin. Right, that is the universal gas constant. The universal gas constant I am marking as RU, given 8314, right, 0.3, right, joule per kilomole Kelvin. You are asked to decide what is the increase in entropy due to mixing process. No temperature difference, no pressure difference, but two dissimilar gases are mixing. If the 2 gases are similar gases, like left side compartment and right side compartment both are maintaining the nitrogen gas, similar gases. By the time the 2 similar gases are mixing, the entropy change due to mixing is 0. But here dissimilar gases are there. Because of the mixing of the dissimilar gases, entropy always increasing. That increase in entropy due to mixing, the entropy change due to mixing equal to minus of number of moles, total number of moles, into RU, universal gas constant, into number of moles of the nitrogen gas, into Ln, number of moles of the nitrogen gas, plus number of, not number of moles actually, mole fraction, that is a mole fraction, not number of moles, 1 minute, mole fraction, 1 minute, Y for N2, Y is for mole fraction, plus mole fraction for CO2 into Ln mole fraction for CO2, Y for CO2. That is the question, that is the right formula for this. Here the mole fraction for N2 equal to number of moles of N2 divided by number of moles of N2 plus number of moles of CO2. Each compartment is maintaining 1 kilomole only, it is 1 by 2 simply. Therefore, Y for N2 equal to Y for CO2, mole fraction remains same at 1 by 2, 0.5, right. So, it is equal total number of moles means total number of moles N equal to N of the N2 plus N of the CO2, it is equal to 2, Here it is minus 2 into Ru given, look at the Ru value 8314.3, 8314.3 joules per kilomole Kelvin. Y for N2 1 by 2, Ln 1 by 2 plus Y for CO2, mole fraction for CO2 also 1 by 2, Ln 1 by 2. You simplify this value with your calculator. For getting, my calculator has shown, right, here it is 11.52, my calculator has shown kilojoules per Kelvin, that is the value my calculator has shown 11.52, right, kilojoules per Kelvin, that is the answer. I hope all of you clearly understood. So, here there is no change in entropy due to pressure difference, because pressure difference is 0, pressure difference is 0, temperature difference is also 0. Therefore, no change in entropy due to temperature and no change in entropy due to pressure. But the entropy increment is possible. Due to mixing of the dissimilar gases. Though the formula is with negative sign, if you calculate it, it is giving the positive only, because mixing process itself is a irreversible process. Because of the irreversibility in the process, entropy always increasing. Entropy increasing means the change in entropy positive. The reason why we are getting, your calculator shows positive values, this ln fractional value itself is negative. So, this quantity is negative, this quantity also negative, that means this whole quantity is negative. Negative quantity multiplied with negative quantity positive, that means entropy change always positive due to irreversibility in the mixing process. I hope all of you clearly understood or not? Yes. Similarly, look at the next question asked in the year 2000, like this: when an ideal gas with constant specific heats is throttled, ideal gas throttling, when the ideal gas is throttling, for ideal gas, no, in the throttling process, what is remaining constant? Enthalpy remains constant. It means H1 equal to H2. For ideal gas, H1 equal to Cp into T1, Cp into T2, Cp is cancelled. For ideal gas, Cp remains same. Ideal gas are maintaining constant specific heats. T1 equal to T2. T1 equal to T2 means dt equal to 0 for ideal gas during the throttling process. dt 0, dH also 0. But throttling process is the adiabatic process, steady flow adiabatic process, but it is highly irreversible process. The reason why the throttling process is coming under irreversible process, in the throttling process, pressure is decreasing, pressure of the working material is decreasing due to friction. Friction is causing for dropping the pressure of the working material in the throttling process. Therefore, throttling process always coming under irreversible process. Because of the irreversibility in the nature, entropy change always greater than 0. That means entropy always increasing in the irreversible process, like free expansion process and throttling process. Dear friends, remember, free expansion process is the irreversible process for a closed system, whereas throttling process is the irreversible process for steady flow system. Similarly, wire drawing process is also coming under irreversible process. So, because of the irreversibility in any process, entropy change always positive. Now, look at the options. dH 0 correct, dt 0, this is correct, dH greater than 0, it is not correct, dH 0, delta S greater than 0, right. A and D, option A and D are absolutely correct. Understood clearly? That is about the very old question solutions from the first law of thermodynamics. I hope all of you clearly understood or not? Yes. Dear students, now let us discuss the detailed solutions from the questions asked second law of thermodynamics. Okay, Look at the very first question asked in the year 1992 as 1 mark question. It is asking like this: a condenser of a refrigeration system rejects heat at a rate of 120 kilowatts. Given that heat rejection in the condenser is 120 kilowatts, while its compressor consumes 30 kilowatts. The work required for compressor connected to refrigerator is 30 kilowatts. The coefficient of performance of the system, COP, you are asked to decide. Okay, as you know, the COP equal to what? Refrigeration effect dividing by work input to the compressor. Here refrigeration effect can be decided like this: the work input to the compression equal to heat rejection in the condenser minus refrigeration effect. From this, the refrigeration effect equal to heat rejection in the condenser minus work required for compressing the refrigerant. Heat rejection in the condenser given 120 minus compression work is 30. 120 minus 30, 90. That is the refrigeration effect. It is in kilowatts. It is equal to 90 divided by 30 gives 3. That is the COP of the refrigeration system. Look at the option D. Option D is absolutely correct. Okay. Similarly, look at the another question. A reversible heat transfer demands, dear friends, remember the heat transfer with large temperature difference or large temperature gradient always coming under irreversible heat transfer. But the heat transfer with very small temperature difference, that is infinitesimally small temperature difference, is coming under reversible process. Look at the options. The temperature difference causing heat transfer tends to 0. Absolutely correct. The heat transfer due to very small temperature difference is treated as a reversible process. Similarly, the expansion process with very small pressure difference is also treated as a reversible expansion process. Anyhow, A is correct. Similarly, look at the next one, asking like this: any thermodynamic cycle operating between two temperature limits is reversible if the product of the efficiency when operating as a heat engine and COP when operating as a refrigerator is equal to 1. You are asked to decide, is it true or false? That means there is a refrigerator and heat engine, both are operating for the same temperature limits. What is the product of COP of refrigerator and efficiency of the heat engine, right? Is it equal to 1 or other than 1? For that, as you know, COP of refrigerator is equal to lowest temperature by highest temperature minus lowest temperature. For the same temperature limits, efficiency of the heat engine is highest temperature minus lowest temperature by highest temperature. Then the product of these two quantities, the COP of the refrigerator multiplied by efficiency of the heat engine, is equal to COP of refrigerator TL by TH minus TL into the efficiency of the heat engine TH minus TL divided by TH. As you know, these two quantities are cancelled. Finally, it is equal to lowest absolute temperature by highest absolute temperature. You know, lowest absolute temperature means TL is less than TH. Since TL is less than TH, it is less than 1 or it is a fractional value. Therefore, since it is given the product equal to 1, that is false. false is the correct. Understood clearly? Yes. Similarly, look at the another question asking like this. Consider a refrigerator and heat pump working on the reversed Carnot cycle between the same temperature limits. Which of the following is correct? You know, for the same temperature limits, the relation between the COP of the heat pump and COP of the refrigerator is COP of the heat pump equal to 1 plus COP of the refrigerator. Therefore, the COP of the refrigerator, I can write like this: COP of the refrigerator is equal to COP of the heat pump, COP of the heat pump minus 1. That is the relation between the COP of the refrigerator and COP of the heat pump when both are working for the same temperature limits. Look at the option C. COP of refrigerator is equal to COP of the heat pump minus 1. Option C is absolutely correct. Okay. Are you following clearly? Yes. Then look at the next one. In the case of a refrigeration system undergoing irreversible cycle, you know, vapor compression, refrigeration cycle is coming under irreversible cycle. The reason is vapor compression refrigeration cycle is working with the throttling process. Throttling process is highly irreversible process. Anyhow, the Clausius inequality equation is cyclic integral del q by t always less than or equal to 0. That means cyclic integral del q by t is equal to 0 for a reversible cycle. For a reversible cycle, whereas cyclic integral del q by t is less than 0 for any irreversible cycle. For any irreversible cycle. Dear friends, remember cyclic integral del q by t greater than 0 is impossible. Is impossible. That means for a reversible cycle, cyclic integral del q by t equal to 0. But for irreversible cycle, cyclic integral del q by t less than 0, correct, because it is given for irreversible cycle. Anyhow, cyclic integral del q by t less than 0 for all irreversible cycle like vapor compression refrigeration cycle. Whereas for Otto cycle is coming under reversible cycle. For Otto cycle, diesel cycle, dual cycle, Stirling cycle, Rankine cycle, these are all the reversible cycles. For all these reversible cycles, cyclic integral del q by t equal to 0. Okay, understood clearly? Yes. Then look at the 2 marks question asking like this. Round the clock cooling of an apartment having a load of 300 megajoules per day requires an air conditioning plant capacity. That means to remove this much amount of heat from the apartment, what is the capacity of the refrigeration system or air conditioning unit must be required. For that, let us decide the refrigeration effect. Refrigeration effect equal to what? That means the amount of heat to be removed equal to 300. Since it is in megajoules, multiply with 10 power 3 to get in kilojoules per day. Per day means 24 hours, right? 1 hour equal to 60 minutes, then it gives kilojoules per minute. You simplify this value with your calculator. Your calculator may be showing around 208.8 kilojoules per minute. As we all know, 1 ton refrigeration effect equal to 210 kilojoules per minute. Since 1 ton refrigeration effect equal to 210 kilojoules per minute, refrigeration effect required is approximately equal to 210. Therefore, the capacity of the unit is around 1 ton. Therefore, you can select the option A. That means for this apartment, you need to select the air conditioning unit which should be maintaining the 1 ton capacity. Then only the apartment people can feel comfortable by removal of that much amount of heat. Understood clearly? Yes. Similarly, look at the next question asking like this. A solar energy based heat engine which receives 80 kilojoules of heat at 100 degrees centigrade rejects 70 kilojoules of heat to the ambient temperature is to be designed the thermal efficiency of the heat engine. As you know, thermal efficiency of the heat engine is equal to 1 minus heat rejection by heat supplied into 100. It is equal to 1 minus, look at the amount of heat rejection, 70. 70 divided by amount of heat supplied, 80, into 100. You simplify this value for getting the answer around 12.5%. That is the heat engine efficiency. Whereas the Carnot heat engine efficiency depends on only minimum temperature and maximum temperature. 1 minus, look at the minimum temperature. Minimum temperature is 30 plus 273. Temperature must be in Kelvin, dividing by the temperature where the heat supplied is 100. 100 plus 273. Operate your calculator and multiply with 100 for getting in percentage. My calculator has shown 18.7%. Since the heat engine efficiency less than maximum possible efficiency, that is Carnot cycle efficiency, it is a possible engine. And engine efficiency equal 12.5%, right? So it is determinant engine, not indeterminate, right? Because the heat engine efficiency less than Carnot cycle efficiency. The actual efficiency of the heat engine is 12.5, but maximum possible efficiency is 18.7, that is equal to Carnot cycle efficiency. Therefore, you can opt the option C. Understood clearly? Yes. Similarly, look at the next question asking like this. For two cycles coupled in series, the topping cycle has efficiency of 30% and bottoming cycle has efficiency of 20%. Overall efficiency of the combined cycles. That means he is telling that two Carnot cycles are arranged in series with first cycle efficiency how much? 30%, right? 0.3, and second cycle efficiency 20%, equivalent to 0.2. Then what is the combined cycle efficiency? That is the overall efficiency how much? Very simple. As you know, overall efficiency equal to eta 1 efficiency of the first Carnot cycle plus efficiency of the second Carnot cycle minus eta 1 eta 2, eta 1 plus eta 2, right, into eta 2. Eta 1 0.3 plus 0.2 minus 0.3 into 0.2. You operate your calculator and simplify it for getting it is 0.44. That is the value my calculator has shown. In percentage, it is 44%. That is the combined efficiency of the series arrangement of the two Carnot cycles. Look at the option B. Option B is absolutely correct. Understood clearly? Yes. That's all about the second law of thermodynamics. Okay na? Yes. Dear students, now let us discuss the detailed solutions for the unit on which where the students are generally feeling it is difficult, that is entropy. In fact, the concept of entropy is very easy, but students are feeling that it is difficult unit. Okay. Anyhow, let us take the 1 mark questions. Look at the very first question asked in the year 1993. It is asking like this: which among the following relations is/are valid only for reversible process undergone by a pure substance? It is asking only for a reversible process. Okay. Here it is given in terms of del Q, TdS, etc. As you know, non-flow energy equation is del Q equal to del W plus du. Here heat and work are path function quantities. Path function quantities are operated by inexact differential, that is del, whereas U is the internal energy operated by the d, because internal energy is coming under property. All properties are coming under thermodynamic system point function quantities. That means point function quantities are operated by the letter D and path function quantities are operated by the letter del. Okay. Remember, this equation is valid for both reversible and irreversible process undergone in any closed system. Okay. But as you know, del W equal to P dV only for a reversible process. Del W for a reversible process is equal to P dV. Then if I write P dV in the place of del W, P dV plus du. This particular equation is valid for only reversible process undergone in any closed system, because the quantity P dV equal to work done only for a reversible process. So it is for both reversible and irreversible process. It is for only reversible process. Okay. But as you know, ds for a reversible process is equal to del q by t. From this del q equal to TdS. But what is the del q? Del q equal to del W plus du. Del q equal to TdS for a reversible process. Del W equal to P dV for a reversible process plus du. Remember, U is the internal energy, it is a property of the system. Property does not care the reversibilities or irreversibilities of the process. Once the system reaches to final state from the initial state, the property change remains same, but path function quantities like del Q and del W are changing. Anyhow, look at the last relation. Though del Q equal TdS only for a reversible process, and del W equal to P dV also only for a reversible process or for reversible process. Look at the resultant relation. The resultant equation is maintaining only properties: T property, S property, P property, V property, U property. Since the resultant equation is maintaining only properties, the equation which is maintaining only properties valid for all process, means for both reversible and irreversible process undergone in any closed system. Anyhow, this equation is valid for both reversible process and irreversible process undergone in any closed system. Whereas this equation is valid for only reversible process undergone in any closed system. This equation is valid for both reversible process and irreversible process, right? Anyhow, since it is asked for only reversible process, for only reversible process del Q must be equal to P dV plus du. Therefore, option D is absolutely correct. Understood clearly? Yes. Similarly, look at the another question. When a system executes in irreversible cycle, as you know, cyclic integral del Q by T less than or equal to 0, that is called Clausius inequality equation. Cyclic integral del Q by T is equal to 0 for a reversible process. Cyclic integral del Q by T less than 0 for irreversible process. For irreversible process, cyclic integral del q by t greater than 0 impossible. Cyclic integral del q by t more than 0 impossible. Since it is asking for irreversible process, del q by t with cyclic integral must be less than 0. Cyclic integral del q by t less than 0. Therefore, option A itself is absolutely correct. Okay. The best example for thermodynamic irreversible cycle is vapor compression refrigeration cycle. You know, the vapor compression refrigeration cycle is for the vapor compression refrigeration system. Generally, vapor compression refrigeration system is constructed with the throttling valve for dropping the pressure of the refrigerant. Throttling process is highly irreversible process. If one process is irreversible for a cycle or all the processes are irreversible for a cycle, that kind of cycle is coming under irreversible cycle. For that kind of irreversible cycle, cyclic integral del q by t less than 0. Whereas for Carnot cycle, Otto cycle, Rankine cycle, Brayton cycle, Atkinson cycle, Stirling cycle, Lenoir cycle, Erickson's, these are all the reversible cycle. For all these reversible cycles, cyclic integral del q by t is equal to 0. Cyclic integral del q by t is equal to 0. Anyhow, since it is asked for irreversible cycle, cyclic integral del q by t less than 0. Okay? Yes. Similarly, look at the next one. It is asking like this. The slopes of constant volume and constant pressure lines in the TS diagram respectively. The slopes of the constant volume curve and constant pressure curve. First, let me take the constant volume process. For a constant volume process, del q equal to Cv into dt. But for a reversible process, constant volume process is a reversible process. For a reversible process, del q equal to Tds. For any reversible process, del q equal to Tds equal to Cv into dt. From this, the quantity dt by ds is equal to T by Cv. So, this is the slope of the constant volume curve in the TS diagram. The slope is T by Cv. The slope of the constant volume curve is T by Cv. Now, come to the constant pressure process. This constant pressure process also a reversible process. Constant volume process, constant pressure process, constant temperature process, reversible adiabatic process, polytropic process. For all these process, right, for all these process, the del q equal to Tds, because all these processes are coming under reversible process. Anyhow, for the constant pressure process, heat transfer q equal to Cp into dt. Cp into dt. Since it is a reversible process, for any reversible process, del q equal to Tds equal to Cp into dt. From this, you can write that the dt by ds at constant pressure is equal to T by Cp. This is the slope of the constant pressure curve in the TS diagram. This is the slope of the constant volume curve in the TS diagram. From this, the conclusion is dt by ds at constant volume, right, is more than dt by ds at constant pressure, because the Cv is less than Cp. That means while we are constructing the TS diagram for Otto cycle and diesel cycle, for the Otto cycle, constant volume heat addition curve must be drawn with a slope T by Cv, whereas constant pressure curve must be drawn in the TS diagram of the diesel cycle with a slope T by Cp, because for the diesel cycle, heat must be added at constant pressure, whereas for Otto cycle, heat must be supplied at constant volume. Understood clearly? Yes. Similarly, look at the next one. It is asking like this. A 1500 watts electrical heater is used to heat 20 kg of water specific heat given in joules per kg Kelvin in an insulated bucket. Insulated bucket means the electrical energy which is converted to heat energy is completely utilized for heating the water because bucket is perfectly insulated. That means no heat is going out. From a temperature of 30 degrees centigrade to 80 degrees centigrade. Okay, by the time the heat energy is transferring to water from the electrical heater, temperature of the water is increasing from 30 degrees centigrade to 80 degrees centigrade. Okay. If the heater temperature is only infinitesimally larger than the water temperature during the process, it means indirectly temperature of the heater remains constant. Temperature of the heater remains constant. But look at the water data for water, mass of the water given 20 kilograms, specific heat of the water given 4186 joules per kg Kelvin, and initial temperature of water T1W given 30, it is 30 plus 273 equal to 303 Kelvin. The final temperature of water is equal to 80 plus 273, it is equal to 353 Kelvin. Okay. Since the heater is maintaining constant temperature, you are asked to decide the change in entropy of the heater and change in entropy of water, which is in joules per Kelvin. First, let me take the change in entropy of the heater. For heater, you know, ds, heater is the body, solid body. For both solids and liquids, entropy change formula is same, that is mass of the material, Cp of the material, Ln, final temperature of the material dividing by initial temperature of the material. For the heater, temperature remains constant means final temperature and initial temperature both are equal, therefore this part is becoming 1. What is the Ln1 value? Ln1 equal to 0, 0 and something 0, therefore the change in entropy of the heater is 0. Change in entropy of the heater is 0. Now come to the change in entropy of the water. Water is the liquid. For the liquid's change in entropy, right, formula being same, for water, this is for water. For water, the change in entropy ds equal to mass of the water into Cp of the water into Ln, final temperature of water dividing by initial temperature of water. Mass of the water given 20 kilograms, look at the value, Cp 4186, Ln T2, look at the T2, 80 plus 273, 353 by 303, 353 by 303. Operate your calculator to get the answer. My calculator has shown the answer 12787 joules per Kelvin. That is the answer, right? My calculator has shown that is the answer. That is the change in entropy of water. 12787. 12787. That is the answer. I hope all of you clearly understood. I am trying to explain the each and every point at your easily understanding level. Okay. Shall I take the next one? Yes. Look at the next one. It is asking like this. For an ideal gas, the expression T dou S by dou T at constant pressure minus T dou S by dou T at constant volume is always equal to the gas constant R. Gas constant R, because you know the del Q at constant volume is equal to Cv dt. Okay, but del Q equal to what? TdS. Del Q equal to TdS for a reversible process, because constant volume process is the reversible process. TdS equal to Cv into dt. From this, T into ds by dt at constant volume equal to Cv. It can be also written as T into dou S by dou T at constant volume is equal to Cv, that is the specific heat at constant volume. Similarly, look at the constant pressure process. For a constant pressure process, this is for a constant volume process. Both constant volume process and constant pressure process are reversible process. For the constant pressure process, del Q equal to right TdS, but the amount of heat transfer at constant pressure equal to Cp into dt. From this, T into ds by dt at constant pressure is equal to Cp, or T into dou S by dou T at constant pressure is equal to Cp. So, T dou S by dou T at constant pressure, this is equal to Cp minus T dou S by dou T at constant volume equal to Cv. What is the Cp minus Cv? Equal to R, that is the Mayer's equation. That means indirectly this quantity equal to Cp, this quantity equal to Cv, Cp minus Cv equal to R. R is called characteristic gas constant. Therefore, option C is absolutely correct. Okay, understood clearly? Yes. Similarly, look at the another question asking like this: a system undergoes a state change from 1 to 2 according to the second law of thermodynamics. For the process to be feasible, the entropy change, that is S2 minus S1 of the system. You know, by the time the process is happening with the system, the change in entropy of the system may be positive or negative or 0. Similarly, change in entropy of the surroundings may be positive or negative or 0. But some of the system change in entropy and surroundings change in entropy is the universe change in entropy. That universe change in entropy, always greater than or equal to 0. Universe change in entropy never be negative. That means universe entropy cannot be decreasing. Universe entropy may be increasing with irreversibilities in the process, or equal to 0 with all reversible process connected to universe. Anyhow, since it is asking for the system change in entropy may be positive or negative or 0. Therefore, you can opt the D. Change in entropy of the system may be positive or negative or 0. Similarly, change in entropy of the surroundings also may be positive or negative or 0. But combined effect of system change in entropy and surroundings change in entropy must be more than or equal to 0. Right? It is like this. Let us take the system. Let us take the system. If the system is working with a reversible process and insulated means del Q equal to 0. Del Q equal to 0 and the process connected to system reversible means all irreversibility is 0. Then ds equal to what? ds equal to del Q by T plus entropy generation. Okay. If irreversibilities are 0, entropy generation 0. If the system is insulated, del Q 0, then ds equal to change in entropy equal to 0. Okay. But even if the process is reversible, if the process is reversible, entropy generation is equal to 0. Entropy generation is equal to 0. Let me write it clearly. Entropy generation equal to 0 for a reversible process. But if the system is not insulated, that means if the heat is entering to the system, then ds equal to what? ds equal to del Q by T for that reversible heat transfer. Since the heat entering to the system is positive, del Q is positive, positive by temperature of the system, right, increasing the entropy. Entropy change is positive. Similarly, if the system is losing the heat energy, the ds equal to del Q by T. Since the system is losing the heat energy, del Q is coming under negative. This value is negative. If del Q is negative, definitely change in entropy is negative. From this you can conclude that change in entropy of the system may be either positive, right, or negative or 0. Right. Similarly, change in entropy of the surroundings also may be positive or negative or 0, but universe change in entropy always more than or equal to 0. Since it is asked for the system change in entropy may be positive or negative or 0. That is why we opted D. Understood clearly? Yes. Similarly, look at the another question. Look at this question. It is asking like this. Figure below shows a reversible heat engine. For a reversible heat engine, Clausius inequality cyclic integral del Q by T is equal to 0. Okay. Having heat interactions with 3 constant temperature systems, calculate the thermal efficiency of the heat engine. Though this is a reversible heat engine, since it is operating with more than 2 thermal reservoirs, you cannot use the temperature limits for finding the efficiency. Efficiency equal to 1 minus T minimum by T maximum. Efficiency equal to 1 minus T minimum by T maximum. This formula can be used only for a reversible heat engine operating between the 2 thermal reservoir limits. Though this fellow is a reversible heat engine, since it is working with more than 2 reservoirs, thermal reservoirs, this formula is not valid for this particular problem. Therefore, I have to use the formula efficiency of the reversible heat engine, I should use 1 minus heat rejection dividing by total heat supplied. That formula can be used for any heat engine. Look at the heat engine. Q1 is supplied to the heat engine, therefore this is the positive. Q2 is also supplied heat, that is also positive. Therefore, total heat supplied equal to Q1 plus Q2. Heat is 100 plus 50, 150. This is the total heat supply, 150 kilojoules. Heat rejection, this is the heat rejection. That heat rejection is not given, but you can find by applying the Clausius inequality equation. It is like this. So, cyclic integral del Q by T equal to 0 for any reversible cycle, right. It is equal to Q1 by T1, it is a positive quantity, plus Q2 by T2, it is also a positive quantity because Q1 and Q2 are the supplied heats, thermodynamically heat supplied system taken as positive, but Q3 is the rejecting heat is negative. Q3 by T3 is equal to 0. Look at the Q1 is 100, T1 1000, 100 by 1000, 100 by 1000, listen carefully, plus Q2, look at the Q2 is 50 by 500, 50 by 500, minus Q3, what is the T3? 300, must be equal to 0. 100 by 1000, 0.1, 50 by 500 also 0.1, it is equal to Q3 by 300. 0.2 is equal to Q3 by 300. From this Q3 equal to 0.2 into 300. It is equal to 60 kilojoules. That is the heat rejection. Then efficiency of the reversible heat engine, which is operating with 3 reservoirs, 1 minus heat rejection Q3 by heat supplied is Q1 plus Q2, it is equal to 1 minus Q3 60 dividing by 150, okay, right, dividing by 150, it is giving right. So, operate your calculator for getting, of course, here it is 0, 3, 2, 3, 5, right. 1 minus it is equal to 1 minute, it is equal to 1 minus 2 by 5, 2 by 5 equal to 0.4, 1 minus 0.4, 1 minus 0.4, 0.6 equal to 60%, right, 60%. Options are not available. Anyhow, thermal efficiency of the heat engine is equal to 60%. That is the answer. Understood clearly? Yes. Similarly, this is the 2 marks question. It is asked in the year 93. Okay. Similarly, look at the next question. It is asking in the year, it was asked in the year 95, asking like this: 1 kilomole of an ideal gas, number of moles of ideal gas 1, is throttled from initial pressure. It is for throttling process. Throttling process is highly irreversible process. Initial pressure P1 equal to 0.5 megapascal, 0.5 megapascal. The final pressure P2 equal to 0.1 megapascal. The initial temperature is 300 Kelvin. Initial temperature T1 is equal to 300 Kelvin. 300 Kelvin. The entropy change of the universe. Right, the surrounding change in entropy for the throttling process, because throttling process is the highly irreversible process, but it is adiabatic process. It is like this: the flow of working fluid through the small restricted passage is called throttling process. For showing the restriction in the flow, I am placing a valve like arrangement. Valve is also perfectly insulated. Since the system is insulated, heat transfer to surroundings is 0. Since the heat transfer to surroundings is 0, entropy change of the surroundings is equal to 0. Entropy change of the surroundings 0. Next, entropy change of the system. Entropy change of the system minus N into Ru. In terms of number of moles, it should be universal gas constant, minus N into Ru, right, ln P2 by P1. P2 by P1. Number of moles 1 minus 1. Ru 8.314 kilojoules per kilomole. ln P2, look at the P2 value. P2 value 0.1, P1 0.5. ln 0.1 by 0.5. 0.1 by 0.5. You simplify your calculator for getting. This is a fractional value. ln fractional value is negative. Negative quantity with negative quantity, positive. Entropy change in the throttling process always positive because it is irreversible process. My calculator has shown 13.38. 13.38 kilojoules per kilomole Kelvin, because number of moles are 1. Kilojoules per kilomole Kelvin. That is entropy change of the system. He is asking entropy change of the universe. Entropy change of the universe equal to entropy change of the system plus entropy change of the surroundings. Since entropy change of the surroundings is 0, right? So, entropy change of the universe itself equal to system change in entropy, that is 13.38 kilojoules per kg mole Kelvin, kilomole Kelvin or kg mole Kelvin. That is the answer, right? So, right, anyhow, right, the kg mole, right, he might be taken this, N is in kilomole, Ru is in kilojoules per kilomole Kelvin, right. He might be cancelled the kilomole and kilomole, but since it is decided with 1 kilomole only, you can also write the same value kilojoules per kilomole Kelvin. Anyhow, The answer is right 13.38 kilojoules per kilomole Kelvin. Option A itself is absolutely correct, right? See, though you multiply with number of moles, since number of moles are one only, it can be written either kilojoules per Kelvin or kilojoules per kilomole Kelvin, right? With this, right, the problems, I am concluding the problems which were given before 2000 in the most important unit, that is entropy, right? I hope all of you clearly understood. Understood or not? Yes. Dear students, now let us discuss the solutions for the properties of pure substances. Okay. First, let us take the 1 mark questions. Look at the very first question asked in the year 1993 like this. The relationship dou T by dou P at constant enthalpy equal to 0 holds good for, you know, that quantity equal to Joule-Thomson coefficient. Joule-Thomson coefficient mu Jt equal to dou T by dou P at constant enthalpy. Dear friends, remember, Joule-Thomson coefficient is the slope of isenthalpic curve, that means constant enthalpy curve, in the temperature versus pressure coordinate system for a throttling process. Okay, it is like this. Let us take the temperature on the y-axis, pressure on the x-axis. You know, in the throttling process, pressure of the working fluid continuously decreasing due to friction. Since friction is causing for dropping the pressure in the throttling process, wherever the friction effect is considered, that process is coming under irreversible process. From that, the conclusion is throttling process is highly irreversible process. This process is used for dropping the pressure, right? This may be the initial state of the working fluid and this may be the final state of the working fluid, and the change in state, that you can say process, the process is happening irreversibly like this. That is how the process is happening. Let me mark it clearly. That is the final state. Since it is irreversible process, mark it with a broken line. Look at the pressure in the throttling process. Pressure keep on decreasing. Pressure keep on decreasing means dou P always negative. Change in pressure always negative in the throttling process. But look at the temperature. In the first half of the process up to this particular state, temperature is increasing. That means in this region temperature increases means dou T positive. Okay. For that, this is the state K. For the 1 to K, look at the Joule-Thomson coefficient mu Jt equal to dou T by dou P at constant enthalpy. This dou P is negative. For the 1 to K, dou T is positive. Positive by negative, Joule-Thomson coefficient is negative for the first half throttling process, right? That process we are calling as warming process. The reason why it is called warming process is temperature is increasing. Okay. Generally in the thermodynamics, the increase in temperature is caused by heating process or warming process. Okay. But look at the K to 2 process. Look at the K to 2 process. For the K to 2 process, right, look at the temperature. Temperature is decreasing. That means dou T is negative. The Joule-Thomson coefficient mu Jt equal to dou T by dou P at constant enthalpy. For the K to 2, that is the second half process, dou T negative, dou P negative. Therefore, Joule-Thomson coefficient is positive. That process we are calling as cooling process. This is the cooling process. Cooling process means why this process is called cooling process? Temperature decreases. Anyhow, the throttling process can be completed by the combined effect of warming and cooling. For the warming process, Joule-Thomson coefficient is negative. For the cooling process, Joule-Thomson coefficient is positive. But look at the apex point. The slope of the isenthalpic curve is changing from negative to positive or positive to negative. That particular point we are calling as inversion point. Inversion point. At that inversion point, where the temperature change from negative to positive or positive to negative, the Joule-Thomson coefficient mu Jt equal to 0. At the inversion point, temperature change is changing from positive to negative or in the reverse direction negative to positive. Therefore, that particular point we are calling as inversion point. At the inversion point for any working fluid, Joule-Thomson coefficient mu Jt is 0. That is the answer. Look at the options. An ideal gas at any state, a real gas at any state, any gas at critical state, any gas at its inversion point. Option D is absolutely correct. But remember, for ideal gas also, Joule-Thomson coefficient 0, because in the throttling process, enthalpy remains constant. Enthalpy remains constant means what? H1 equal to H2. Enthalpy before throttling equal to enthalpy after throttling. For ideal gas, enthalpy depending on only temperature can be written as Cp T1 equal to Cp T2. From this I can write that T1 equal to T2. Temperature remains constant if the ideal gas is throttling. Therefore, what is the dou T value? Dou T value 0. Then for ideal gas, Joule-Thomson coefficient mu Jt equal to dou T by dou P at constant enthalpy. Since temperature remains constant in the throttling process with ideal gas, Joule-Thomson coefficient is 0 for ideal gas. Okay. Since Joule-Thomson coefficient 0 for ideal gas, right? If the ideal gas is the working fluid, you should not select the throttling device for dropping the pressure. That means the ideal gas are not supporting for throttling process. Let us take the bootstrap air refrigeration system or Bell-Coleman air refrigeration system. For Bell-Coleman refrigeration system or bootstrap air refrigeration system, air is the refrigerant which is coming under ideal gas. Since the ideal gas like atmospheric air is the refrigerant for Bell-Coleman cycle, we are not using the throttling device for dropping the pressure. In the place of throttling device, we are using the expander like gas turbine for dropping the pressure. That means if ideal gas like atmospheric air is the refrigerant, you have to select the expander for dropping the pressure because the ideal gas are not supporting for throttling process. Anyhow, for ideal gas also the quantity is becoming 0, the Joule-Thomson coefficient is 0, but among the A and D, right, most appropriate answer is D only, right. That is why I selected the D correct. Understood clearly? Yes. Similarly, look at the another question. It is asking like this. During the phase change of a pure substance, during the phase change process, sublimation, desublimation, evaporation, condensation, freezing, melting, these are the phase change process. For the phase change process, remember dg equal to 0, that is change in Gibbs function remains 0 and change in pressure also remains 0, right. It is like this. Let us take the temperature versus enthalpy coordinate system. Enthalpy coordinate system. If I take the water at 0 degree centigrade, water is coming under one of the pure substances. If we keep on adding the heat at constant pressure, the amount of heat addition at constant pressure equal to change in enthalpy. By the time we are adding the heat, temperature keep on increasing until it reaches to boiling point. But once it reaches to boiling point, the water starts vaporization. In the entire vaporization process, both pressure and temperature remains constant. So, A to B be the vaporization process. Once all the saturated liquid particles are becoming saturated vapor particles, because of the further heat addition, temperature increases at constant pressure. That is the constant pressure line. Okay. So, in the phase change process for AB, for the A to B, that is the phase change process called vaporization, right? Vaporization. This is the vaporization. For the vaporization process, right, what is the pressure? Pressure remains constant. Pressure remains constant means dP equal to 0. dP equal to 0. Now come to the Gibbs function. As you know, Gibbs function G equal to H minus Ts. H minus Ts. Then dG equal to dH minus Tds minus S dt. Minus S dt. Okay. But what is the H value? H equal to U plus PV. Then dH equal to what? dH equal to du. dH equal to du. dH equal to du plus PdV plus VdP. Plus VdP. dH equal to du plus PdV is the del Q plus VdP. For a reversible process, del Q equal to TdS. Del Q equal to TdS plus VdP. So, in the place of dH, let me write this value. dH equal to TdS plus VdP. dG equal to, right, TdS plus VdP minus TdS minus S dt. Okay, this plus TdS minus TdS cancelled. Finally, dG equal to VdP minus S dt. In the phase change process, like vaporization process, not only pressure constant but also temperature remains constant. Since temperature is constant in the vaporization process, that is the phase change process, dt equal to 0. And pressure also remains constant. Change in pressure is 0. 0 minus 0 equal to 0. From this, the conclusion is, in the phase change process for any pure substances, change in pressure 0 and change in Gibbs function also 0. Of course, change in temperature also, the change in temperature dt also equal to 0 for any pure substance. That is why we opted option A and B. I hope all of you clearly understood. Understood or not? Yes. Then let us take the another question. It is asking like this. At a triple point of a pure substance, the number of degrees of freedom is. Triple point means the point where the three phases of the same material can coexist under equilibrium state is called triple point state. Okay. So, at a triple point state, solid is existing, liquid is existing, vapor is existing. Then, solid is coming under one phase, liquid another phase, vapor another phase. The three phases of the same material can be coexisting. Therefore, number of phases existing at the triple point state 3. Okay. Now, though three phases are existing, the material is single component system. You take the water at the triple point state, the water is existing as a liquid, as a steam and as a ice. Okay. The same water existing, right, as three phases means number of components of the system equal to 1. Then what is the Gibbs phase rule? Number of independent intensive properties required to look at the thermodynamic state equal to C minus P plus 2. Here 2 represents number of basic intensive properties, namely pressure and temperature. Here 2 represents one quantity is pressure and other quantity is temperature. Okay. Now, the degree of freedom F equal to C, look at the C, 1 minus 3 plus 2, right? 1 plus 2, 3 minus 3 equal to 0. Degree of freedom F equal to 0. So, a triple point state for any pure substance, degree of freedom equal to 0. That means we are not the people for deciding the triple point state. It means each and every material is maintaining its unique, right, unique character of the triple point state. That means each and every material is deciding its own or unique triple point state. Okay. Anyhow, a triple point state, degree of freedom equal to 0 for any pure substance like water. Understood clearly? Yes. Then look at another one, asking like this: constant pressure lines in the superheated region in the molar diagram will have the slope of the constant pressure lines, right? As you know, in the molar diagram means HS diagram, enthalpy versus entropy diagram. Enthalpy versus entropy diagram. The saturation curve in the molar diagram available with steam tables is marked like this. That is the saturated vapor curve is marking, right, by passing the enthalpy coordinate through the critical point. This is the critical point. Okay. As you know, the H equal to U plus PV, na? H equal to U plus PV. DH equal to DU plus PdV plus VdP, right, plus VdP. It can be also written as DH equal to DU plus PdV del Q plus VdP. For a constant pressure line, dP equal to 0. When this quantity dP equal to 0, the dH equal to del Q. But del Q for a reversible process, TdS. So, dH equal to TdS. Then dH by ds at constant pressure is equal to T, absolute temperature. The quantity dH by ds at constant pressure is the slope of isobaric line or constant pressure line in the HS coordinate system or molar diagram. That is equal to absolute temperature, absolute saturation temperature. Therefore, the constant pressure line is looking like this. This is the one of the constant pressure line. The constant pressure line is maintaining almost a straight line variation within the saturation dome, but bending upwards in the superheated region. Though the constant pressure line is bending upwards in the superheated region, its slope is positive. Its slope positive means by the time the enthalpy is increasing, entropy also increasing. If I say this is the one constant pressure line, the another constant pressure line may be like this. 1 minute. So, the constant pressure line is almost a straight line within the saturation dome, but bending upwards in the superheated region, P2, right, provided P2 is more than P1. That is how the constant pressure lines are projecting in the molar diagram or HS diagram. Anyhow, in the superheated region, constant pressure lines are curved lines, but they are maintaining positive slope only. It means as the enthalpy increases, entropy also increases. Okay. That means dH and ds, dH is positive, ds also positive, not only in the saturation region, but also in the superheat region. That is why the slope is positive, right. Look at the options: a positive slope, negative slope, zero slope, both positive and negative, no, a positive slope. The constant pressure line either in the saturation region or above the saturation region, no? This is the superheat region. In the superheated region also it is maintaining positive slope. Therefore, option A is absolutely correct. Understood clearly? Yes. Now, look at the another question. Look at this one. It is asking like this: when wet steam flows through a throttle valve and remains wet at exit, wet steam is throttling, final state of the wet steam also wet, right? Then, right, different options are given, like its temperature and quality increases, its temperature decreases but quality increases, its temperature increases but quality decreases, its temperature and quality decreases. Now, let us mark the throttling process for the wet steam becomes wet steam. Throttling process is also called isenthalpic process, right? Means enthalpy remains constant. Look at the HS diagram, is also called Mollier diagram. The saturated vapor curve is looking like this. This is the critical point. Let me mark it clear. We should be very careful while we are discussing in the limited space. This is a critical point, right? In the throttling process, as you know, pressure is dropping. Let the pressure P1 before throttling. After throttling, the pressure of the steam is P2. It is given that wet steam is throttled. This is the wet steam, right? Wet steam is throttled to wet quality only. This is the wet steam throttled to wet steam. That means initial quality and final quality both are remaining same. Okay, that means, right, both are remaining same means initial quality is wet, final quality also wet. But look at the dryness fraction. The dryness fraction at state 1, this is the x1. This is the dryness fraction at state 2, x2. Since this dryness fraction line is very close to saturation curve, along the saturation curve, saturated vapor curve, dryness fraction equal to 1. Since x2 line, right, x2 line is very close to saturation curve, I can say that x2 is more than x1. x2 more than x1 means what? Dryness fraction increases. Okay. Now come to the temperature. Within the saturation dome, isobaric line and isothermal line both are identical. That means corresponding to P1, there is a saturation temperature. Let that is Tsat1. And corresponding to P2, there is a saturation temperature. That is the Tsat. As you know, the P1 is more than P2. Now, what about the saturation temperature? By the time the pressure of the water increases, its boiling point increases. The water starts boiling at 100 degrees centigrade when its surface is maintaining the pressure equal to 1 bar. But when you increase the pressure from 1 bar to 20 bar, definitely boiling point is going to increase. That means with increase in pressure, if the pressure is increasing, its boiling point increases. Boiling point increases means indirectly I can say that saturation temperature increases. Then since P1 is more than P2, I can say that saturation temperature corresponding to P1 is more than saturation temperature corresponding to P2. That means by the time the wet steam is throttled to wet steam, dryness fraction increases but temperature decreases. That is the answer. Now look at the options. Its temperature decreases but quality means dryness fraction increases. Therefore, you can have the option B. Option B is absolutely correct. Understood clearly? Yes. Then look at the 2 marks question. 2 marks question is asking like this. It is also asked in the year 93. Most of the questions are from 93 only. Look at this one. A vessel of volume 1 meter cube. That means total volume of the vessel equal to 1 meter cube. Contains mixture of liquid water and steam. That means a vessel contains wet steam. This is the vessel is maintaining the wet steam. That wet steam is the mixture of liquid and vapor. This vessel volume is given 1 meter cube, that I am written as total volume of the vessel. Next, the pressure of the wet steam given 1 bar. Okay. Given that 90% of the volume is occupied by the steam. That means volume occupied by the steam Vg, Vg equal to 0.9 times the total volume of the vessel. It is equal to 0.9 into 1 equal to 0.9 meter cube. That is the volume occupied by the steam. Otherwise, let me write like this. Volume occupied by the steam. Next, then what is the volume occupied by the liquid? The remaining volume, 100 minus 90%, 0.1 times the total volume of the vessel. It is equal to 0.1 times the 1, that is equal to 0.1 meter cube. So, this is the volume occupied by the steam and this is the volume occupied by the liquid present in the wet steam. Next, the volume occupied by the steam. Find the dryness fraction of the mixture. You are asked to decide the dryness fraction x. X equal to how much? Look at the specific volumes corresponding to 1 bar. Vf given, that is the specific volume of the liquid, right? Vf, specific volume of the liquid given 0.001 meter cube per kg, and specific volume of the vapor marked with Vg. Specific volume of the vapor Vg is given as 1.7 meter, both are in meter cube per kg. Should be very careful while we are discussing in the limited space. These two quantities are in meter cube per kg. Okay. For that, you know the dryness fraction x equal to mass of the steam dividing by mass of the steam plus mass of the liquid. For that, we need to decide mass of the steam and mass of the liquid. Mass of the steam equal to volume occupied by the steam divided by specific volume of the vapor. Specific volume of the vapor. And mass of the liquid equal to volume occupied by the liquid dividing by specific volume of the saturated liquid. What is the volume occupied by the steam? 0.9. 0.9 dividing by specific volume of the steam Vg 1.7. 1.7. Volume occupied by liquid 0.1 dividing by specific volume of the saturated liquid 0.001. 0.001. Now you simplify these values. So this value I am getting 0.1 by 0.00 100 kilograms, that is the mass of the liquid, whereas mass of the steam 0.5294. 0.5294. These are the values shown by calculator, right? Calculator. Then mass of the steam equal to 0.5294 dividing by 0.5294 plus mass of the liquid 100. You simplify this value for getting the answer. My calculator has shown 5.266. 5.266 multiplied by 10 power minus 3. 10 power minus 3, that is the value my calculator has shown. That is the dryness fraction of the steam. 5.266, right, into 10 power minus 3, that is the answer, right. I hope all of you clearly understood. Understood or not? Yes. Then let us take the another question asking like this. In the vicinity of the triple point, the vapor pressure of liquid and solid ammonia, the vapor pressure of the liquid ammonia and solid ammonia, this is the right relation for solid ammonia, right, vapor pressure of liquid and solid. First given value is for liquid, this is for liquid ammonia, and the other relation is for solid ammonia, NH3 respectively, okay, where P is in atmosphere and T is in Kelvin. What is the temperature at the triple point? What is this temperature at the triple point state? Okay, as you know, triple point state means the state where the solid phase, liquid phase and vapor phase of the same material can coexist under equilibrium state is called triple point state. If you take the pressure versus temperature coordinate system, pressure versus temperature coordinate system for water, I am talking about water because each and every material is maintaining its unique triple point state. For water, right, I am talking about water. For water, triple point pressure is 0.00, right, 611 bar, and triple point temperature 0.01 degree centigrade. I am marking for water, mark my point. This is the triple point pressure for water, 0.00611 bar, right, and temperature is 0.01 degree centigrade. Wherever the pressure and temperature are meeting, that is the triple point state. At that triple point state, liquid is existing, that means water is available in the liquid phase, vapor phase, that is steam, and ice phase, that is a solid. The three phases of the same material can coexist under equilibrium state. Though the liquid, steam and ice are existing at that particular state, the three phases of the same material maintaining the same pressure and same temperature. That means liquid water, steam and ice, right, these are three states of the water maintaining same pressure and temperature at the triple point state. Okay, right, it is like this, its meaning is like this. You try to take the water in a vessel, listen carefully. You try to take some water in a vessel. You try to take some water in a vessel. This is the water. Above the water, some space is there. That space is occupied by the atmospheric air. Therefore, atmospheric air pressure is acting on the surface of the water. That atmospheric air pressure may be roughly taken as 1 bar. Now, what I am doing is, I am connecting a vacuum pump here. This is the vacuum pump. For lifting the gas present on the surface of the water. Vacuum pump. This vacuum pump can be lifting the air present on the surface of the water. By the time the air is continuously lifting, right, from the surface of the water, the pressure on the surface of the water keep on reducing. By the time the pressure is keeping on reducing, once the pressure on the surface of the water reaches to 0.00611 bar, once again, once you connect the vacuum pump for lifting the air present on the surface of the water, by the time the vacuum pump is removing the air present on the surface of the water, the pressure which is acting on the surface of the water keep on reducing. Once the pressure on the surface of the water reaches to 0.006 bar, right, assume this water now maintaining the pressure equal to 0.00611 bar. Once the pressure of the water reaches to that value, a part of the water is available as liquid, a part of the water is available as a ice, remaining part of the water is available as steam. That means the three phases of the same material can be coexisting under equilibrium state. That particular state is called triple point state. The pressure at the triple point state is called triple point pressure. Corresponding temperature is called triple point temperature, 0.01 degree centigrade. It means 0.01 degree centigrade is the saturation temperature for water at 0.00611 bar. Anyhow, conclusion is, at a triple point state, the liquid, right, vapor and solid are maintaining same pressure and temperature. Now, you can also mark some different curves, in the sense, this is the sublimation curve, this is the vaporization curve, this is the melting curve for water, this is for water, right, this is the evaporation curve or vaporization curve, and this is the melting curve, and this is the, right, sublimation curve. sublimation curve, right? The melting curve, sublimation curve and vaporization curve, these three curves are meeting only at a triple point state. Okay, from this I can mark that sublimation curve and vaporization curve both are maintaining positive slope and melting curve is maintaining negative slope. That means by the time the pressure is increasing on the surface of the water, its melting temperature decreases. Remember, that is the peculiar property of the ice or water. Anyhow, at a triple point state, my conclusion is, at triple point state, liquid water and that is solid water, that is ice, maintaining same pressure. Similarly, for our problem, right, the relation is given in terms of liquid ammonia and solid ammonia. Since the liquid ammonia and solid ammonia both are maintaining the same pressure at the triple point state, this LNP for liquid must be equal to LNP for solid ammonia. Therefore, 1 minute. For at a triple point state, let me write that point. Liquid ammonia and solid ammonia maintains same pressure. Therefore, whatever the LNP value given for LNP for liquid, must be equal to LNP value given, 1 minute, LNP value given for solid ammonia, Okay. What is the LNP for liquid ammonia? 15.16 minus 3063 by T, 3063 by absolute temperature, it must be equal to 18.70 minus 3754 by T, 3754 by T. Now you simplify it for getting the temperature, right, at the triple point state. My calculator has shown 195.2 Kelvin, because it is given the temperatures in Kelvin, pressure is in atmosphere. So anyhow, answer is 195.2 Kelvin. That is the triple point state of, this is the triple point state of ammonia, right, or triple point state temperature of ammonia equal to 195.2 Kelvin. That is the answer. I hope all of you clearly understood or not? Yes, that is all about the properties of pure substances. Okay, understood clearly? Yes, thank you. Dear students, now let us discuss the solutions for the concept of availability. Only two questions are there which were asked before 2000. One is 1 mark question, the second one is 2 marks question. Okay, look at the 1 mark question asked in the year 2000 like this. Availability of a system at any given state is, a property of the system? No, availability is the combined property of system and surroundings. The maximum work obtainable as the system goes to dead state, it is not maximum work, maximum useful work. The total energy of the system? No. The maximum useful work obtainable as the system goes to dead state? Absolutely correct. The maximum useful work, that is what we are expecting from a system when it is going to dead state, that is atmospheric air state, local atmospheric air state is the availability or exergy or available energy. Anyhow, the maximum useful work obtainable as the system goes to dead state is called availability of the system. Okay, therefore option D absolutely correct. Okay, now look at the 2 marks question asking like this. It is asked in the year 95 like this. A heat reservoir at 900 Kelvin is brought into contact with ambient at 300 Kelvin for a short time. During this period, 9000 kilojoules of heat is lost by the heat reservoir. The total loss of availability due to this process. Loss of availability. According to Gauss-Todler theorem, loss of availability equal to dead state temperature multiplied by a net change in entropy. The dead state temperature is given as ambient temperature. Dead state temperature is the ambient temperature is equal to 300 Kelvin. Okay. Now we need to decide the net entropy change. You know, by the time the 9000 kilojoules of heat is transferring from high temperature reservoir, that is 900 Kelvin to 300 Kelvin, definitely entropy increases. That increase in entropy can be marked like this. Let us take the temperature versus entropy diagram. Temperature versus entropy diagram. The high temperature reservoir is maintaining temperature 900 Kelvin. Let that is T1 equal to 900 Kelvin. Now, the heat is transferring from 900 Kelvin reservoir to 300 Kelvin reservoir. This is the low temperature reservoir, that is ambient temperature T2. T2 equal to 300 Kelvin. Let me mark the heat energy at T1 Kelvin. 1, area below the TS diagram is the heat transfer. I can say area below this 1 to 2 is equal to del Q. That del Q is given 9000 kilojoules. Look at that value, 9000 kilojoules. Okay. Now, this is the entropy change of the reservoir 1 maintaining T1 temperature, right, with 9000 kilojoules. Now, that heat is transferring to low temperature reservoir. For that low temperature reservoir, let this is the state 1 dash, right. Heat energy is conservable quantity. Whatever the heat energy lost by the high temperature reservoir, the same will be reached to low temperature reservoir. Energy is conservable quantity. Therefore, area below 1 to 2 must be equal to area below 1 dash 2 dash, because heat energy is the conservable quantity. Heat energy is a kind of energy. According to first law of thermodynamics, energy cannot be created, cannot be destroyed, but there is a possibility to convert from one kind of energy to other kind of energy. So, I have marked 1 dash 2 dash such that area below 1 to 2 equal to area below 1 dash 2 dash. I am marking like this. Area below 1 to 2 is equal to area below 1 dash 2 dash is equal to heat transfer del Q, that is equal to 9000 kilojoules. That means by the time the heat is transferring from high temperature reservoir to low temperature reservoir, high temperature reservoir is decreasing its entropy, right, whereas low temperature reservoir is gaining its entropy. This is the gain in entropy of the low temperature reservoir, ds corresponding to T2. Then what is the heat gained by, what is the heat gained by, this low temperature reservoir? This is the heat gained by this low temperature reservoir, area below 1 dash 2 dash. Okay. Then ds1, ds corresponding to T1 equal to del Q by T1. Del Q how much? Del Q 9000 divided by T1 900. It is equal to 10 kilojoules per Kelvin. Next, ds corresponding to T2, that is del Q by T2. Del Q by T2. Del Q 9000 divided by what? 300. These two zeros cancelled. 330 times. 30 times. It is equal to 30 kilojoules per Kelvin. While 9000 kilojoules of heat is transferring from 900 Kelvin reservoir to 300 Kelvin reservoir, the high temperature reservoir is losing the entropy equal to 10 kilojoules per Kelvin, right, and increase in entropy in the low temperature reservoir 30 kilojoules per Kelvin, right. Then what is the net change in entropy? Net change in entropy equal to ds corresponding to T2 minus ds corresponding to T1. ds corresponding to 30 minus 10, it is equal to 20 kilojoules per Kelvin. That is the increase in entropy. By the time that the increase in entropy, I can mark like this. So this is the net increase in entropy, ds net. That is the net increase in entropy by the time the heat is transferring from high temperature reservoir to low temperature reservoir. That net increase in entropy multiplied by dead state temperature is giving the loss of availability. That net increase in entropy 20 multiplied by 300, right. So this is equal to 300 multiplied by 20. How much? It is equal to 6000 kilojoules. That is the loss of availability due to transfer of heat from high temperature reservoir to low temperature reservoir. Look at the option C. Option C is absolutely correct. I hope all of you clearly understood. Understood or not? Yes.